Did you know that our planet experiences about 20,000 earthquakes every year? While we go about our daily lives, the earth beneath our feet is constantly shifting and moving. But don't worry, most of these quakes are so small we can't even feel them. Only about 100 of these annual tremors are strong enough to cause damage. The earth isn't as solid as it might appear. It's more like a giant puzzle made up of pieces called tectonic plates. These plates are always on the move, albeit very slowly. They drift apart, collide, and sometimes even slide past each other. This movement is happening right now as you read these words. Now, you might be wondering, what's causing all this movement? Well, it all comes down to heat. Deep within the Earth's core, immense heat causes currents in the semi-liquid mantle. These currents, much like those in a pot of boiling water, cause the tectonic plates floating on top to move. Understanding this restless nature of our planet is crucial. It helps us appreciate the raw power of nature and reminds us of our place in the grand scheme of things. As we delve deeper into the science of earthquakes, we'll uncover the fascinating mechanisms behind these earth-shaking events and learn how we can better prepare for them. An earthquake is the shaking of the Earth's surface. Imagine the Earth's crust as a giant jigsaw puzzle. The pieces are tectonic plates, massive slabs of rock. These plates move slowly, just a few centimeters per year. They interact in various ways, creating stress and strain. When stress becomes too great, the rock breaks along a fault line. This sudden release of energy is what we feel as an earthquake. When an earthquake occurs, it sends out different types of seismic waves. These waves are like messengers carrying information about the earthquake's size and location. There are three main types of seismic waves: P waves, S waves, and surface waves. P waves, or primary waves, are the fastest. They're compression waves moving through the earth like sound waves through air. P waves can travel through both solid rock and liquid, including the earth's core. When P waves pass through, they cause the ground to be pushed and pulled like an accordion. S waves, or secondary waves, are the next to arrive. These are shear waves moving through the earth like a snake. S waves can only travel through solid material, not liquids. This tells us something important about the Earth's structure. The outer core must be liquid because S waves can't pass through it. When S waves pass by, they shake the ground side to side, or up and down, perpendicular to the direction they're traveling. Finally, we have surface waves. As the name suggests, these waves travel along the Earth's surface. They're the slowest of the seismic waves, but they can be the most destructive. Love waves move the ground side to side, while Rayleigh waves cause a rolling motion like ocean waves. These surface waves are what cause most of the shaking we feel during an earthquake, and they're responsible for much of the damage to buildings and infrastructure. Measuring earthquakes is a crucial part of understanding and preparing for these natural events. Scientists use sophisticated instruments called seismographs to detect and record seismic waves. A basic seismograph consists of a heavy weight suspended from a frame. When an earthquake occurs, the frame moves with the ground, but the weight tends to stay still due to inertia. This relative motion is recorded, giving us a visual representation of the earthquake's waves. Modern seismographs are much more complex, using electronic sensors to detect even the slightest ground movements. These instruments are so sensitive, they can pick up earthquakes happening on the other side of the world. Networks of seismographs around the globe work together, allowing scientists to pinpoint the location and depth of an earthquake with remarkable accuracy. But how do we measure the size of an earthquake? That's where the Richter scale comes in. Developed by Charles Richter in the 1930s, this scale measures the magnitude of an earthquake, essentially how much energy it releases. By combining these measurement techniques with our understanding of seismic waves and Earth structure, scientists can quickly assess the potential impact of an earthquake and alert emergency responders. Section 5. Echoes from the past historical earthquakes. Throughout history, earthquakes have left indelible marks on human civilization. One of the most famous historical earthquakes occurred in Lisbon, Portugal, on November 1st, 1755. This massive quake, estimated to have had a magnitude of 8.5 to 9.0, struck on All Saints' Day when many people were in churches. The earthquake, followed by a tsunami and fires, nearly destroyed Lisbon and killed tens of thousands of people. The Lisbon earthquake had a profound impact on European thought. It challenged the optimistic philosophy of the time and led to the development of modern seismology. Philosophers like Voltaire used the event to question the idea of a benevolent God, while others began to seek scientific explanations for such natural disasters. Moving to more recent times, the 1906 San Francisco earthquake stands as a defining moment in American history. This magnitude 7.9 quake ruptured 296 miles of the San Andreas Fault and shook the city for nearly a minute. The quake and subsequent fires destroyed much of San Francisco, killing an estimated 3,000 people and leaving half of the city's population homeless. By studying these historical earthquakes, we gain valuable insights that help us better understand and prepare for future seismic events. Section 6. The Science of Prediction. Predicting earthquakes has long been a holy grail for seismologists. While we've made significant strides in understanding earthquakes, precise prediction remains elusive. However, scientists have developed methods to assess earthquake probability and identify high-risk areas. One key approach is studying the historical seismic activity of a region. By analyzing patterns of past earthquakes, scientists can estimate the likelihood of future events. Another important tool is GPS technology. By precisely measuring the movement of tectonic plates, scientists can identify areas where stress is building up. This helps them pinpoint potential earthquake hotspots. For example, the San Andreas Fault in California is closely monitored using a network of GPS stations. These stations can detect even tiny movements, providing valuable data about the fault's behavior. Seismologists also study foreshocks, smaller earthquakes that sometimes precede a larger one. While not all earthquakes have foreshocks and not all foreshocks lead to larger quakes, they can provide valuable warning signs in some cases. More recently, scientists have been exploring the potential of artificial intelligence in earthquake prediction. Machine learning algorithms can analyze vast amounts of seismic data, potentially identifying patterns that humans might miss. Section 7. Building for resilience. In earthquake-prone regions, construction can mean the difference between life and death. Earthquake-resistant design aims to create structures that withstand seismic forces. The goal is to ensure buildings remain standing and protect occupants. Flexibility is key. Buildings are designed to sway with the motion. Base isolation uses flexible pads to absorb earthquake energy. Shear walls and moment-resisting frames help resist lateral forces. Advanced computer modeling allows engineers to test and refine designs. Section 8. Earthquake preparedness, a life-saving skill. Being prepared for an earthquake can save lives. In earthquake-prone areas, preparedness should be a way of life. Understand the risks in your area. Softer soils can amplify shaking, increasing the risk of damage. Create an emergency kit with essentials like water, food, and first aid supplies. Practice the drop, cover, and hold on technique. Drop to the ground, take cover, and hold on until the shaking stops. Be prepared for aftershocks. By taking these steps, you're helping your community recover more quickly. Section 9. Global impact and response. Earthquakes don't respect national borders. A major seismic event can have far-reaching consequences that extend well beyond the immediate area of impact. The 2004 Indian Ocean earthquake and tsunami, for instance, affected countries thousands of miles apart, from Indonesia to Somalia. This global reach of earthquakes has led to international cooperation in earthquake science and disaster response. Organizations like the United States Geological Survey and the European Mediterranean Seismological Center share data and expertise worldwide, contributing to our global understanding of seismic activity. In the aftermath of a major earthquake, the international community often rallies to provide aid and support. This can include search and rescue teams, medical personnel, and supplies. The United Nations Office for the Coordination of Humanitarian Affairs plays a crucial role in coordinating these international relief efforts. However, the effectiveness of this aid can depend on factors like the affected country's infrastructure and political situation. The global nature of earthquakes has also spurred technological innovations. The Global Seismographic Network, a system of over 150 seismograph stations worldwide, provides real-time data on seismic activity across the globe. This network not only helps in quickly identifying and locating earthquakes, but also contributes to our understanding of the Earth's internal structure.